All right, so thanks very much for having me. My name's Austin Huang, and in this talk, I'm going to be introducing Hasktorch, which is a Haskell library for tensor math and neural networks. And now, before I dive in, though, it's worth asking a question. Where does a language like Haskell fit into the world of machine learning? Because if you look at it to date, there hasn't been that much of a presence of functional programming for machine learning applications. So why is this something that's potentially worth looking to in like a design space that's worth exploring? And to answer that, I think part of that comes from a framing of what are we doing when we work on machine learning projects, machine learning applications? And we need to kind of unroll some of that, our assumptions that are lying that. And so one starting point to think about is there are these stats that get thrown around. So this one's from VentureBeat that supposedly 87% of machine learning models never make it into production, right? And it's worth asking, why is it that that failure rate is so high in sort of making machine learning add value to businesses and to be really kind of successful in transitioning from research to production? I think part of that stems from the way we frame what we're doing when we work with neural networks, when we work on machine learning projects. And kind of the typical conceptual view goes something like this, right? So neural networks are a machine learning algorithm, and they're one among sort of multiple machine learning algorithms like SVMs, k-means, logistic regression. And so neural networks kind of fit into the space of machine learning algorithms, which we study in this field of machine learning, which is in turn a kind of subfield within artificial intelligence, right? And so we think of neural networks as being sort of interchangeable with kind of other algorithms. This kind of our kind of conceptual framing of what we're doing. And I think this view, it's not wrong, but it misses a big aspect of what we're doing in machine learning. And to get some sense as to kind of what's missing there, let's look at something that's actually had a major impact on machine learning. This idea of these transformer architectures, neural network architectures that have really kind of in the past few years transformed the way, no pun intended, we do natural language processing, and right now are in the process of also changing, having a large impact on computer vision as well. Now, to understand this, if you look at something like a transformer architecture, it's not really so much a novelty in an algorithm. So you could write, an equation that sort of reflects the computation of the transformer architecture end to end, but that's not all that enlightening, right? And that's not how you arrive at ideas like this, right? If you kind of look at it, it really looks more like a program with sort of different things that are intended to be composed together to do certain functions. So for example, positional encoding, you could describe it as, okay, you're doing this sine cosine computation, but really kind of the intent of positional encoding is to kind of push the positional information of a token or some piece of data forward into your vector representation that then gets consumed by subsequent pieces in your architecture. And so it's much more useful to think about of an architecture as something that is a system that sort of corresponds to a program. And so you're kind of putting these programs together. One thing that's a little bit different between neural networks and sort of traditional programs is that the final computation that you do is learned. So you can think of a machine learning model as something akin to a curried function, where it is a function that sort of takes parameters as input and returns a function that performs your model inference. This model inference may be the prediction or the classification that you want to do. And you arrive at those parameters that you kind of plug into your model through a training process. That training process is optimizing some objective function known as loss, and takes advantage of the fact that your inference function is end-to-end differentiable using using this automatic differentiation procedure. So you use the automatic differentiation on your model, you can get gradients, and you use that in your training procedure. So you can look at this kind of whole endeavor of machine learning as sort of writing programs that are optimized on data in this way. So we see that kind of have this shift in view that when we're defining a model, we're kind of thinking about it not so much of each architecture being, say, a different algorithm, but each architecture being sort of different ways of composing sort of functional blocks to arrive at sort of new ideas for architectures. If we go sort of one level up in abstraction, these models get trained through some sort of training procedure. And there again, when we talk about sort of different training procedure and sort of innovation in model training, it also corresponds to innovation in building systems. So, for example, as we get to kind of these larger and larger language models that we use in NLP, we need to have sort of systems that make the sort of parallelize sort of the model across multiple devices or parallelize the data across multiple devices. We have sort of new innovations in sort of federating the training to preserve privacy, in which case the training becomes a distributed process among multiple workers. We can also have kind of different ways of combining models with each other through things like distillation, transfer learning. And all of these are sort of different ways of sort of composing new sorts of training processes. We can also insert things like simulators into the loop of the data, into training processes as sort of data generators for the training process. And so you can have entire physics engines, game engines, sort of rendering engines be part of that training loop. And so all of this to say, sort of the training procedure is also all about sort of composing kind of systems of combining data and how you use that data into that optimization that we talked about. When you go to sort of machine learning applications themselves are distributed systems. So we start from kind of our model development process to train, and we then embed our trained model into some sort of runtime. Usually there's some API that wraps the model, and the way you pass kind of a model from training to production is to, say, take a serialized representation of the model computation and then put that into an API endpoint, right? And often you may have some edge consumers of that. So maybe your API service is serving a mobile app or a web app that does something with computer vision, or you have some embedded system. The model can also go can also be deployed all the way to the edge sometimes to do the model computation, say in the browser or on some embedded device. And finally, you have some feedback of data coming back and from these services and coming back to update your model. So you can think about sort of different machine learning applications as sort of special cases of this. So for example, something like a large language model API like GPT-3, or you have some service for Codex, you can think about, okay, I have this large model and I operationalize it as an API. You can think about sort of autonomous driving systems where your model gets sort of pushed to this embedded edge runtime, and it's supported, has some supporting APIs to capture feedback data. Or you can think about sort of privacy preserving API where you might actually do sort of training on your client. And so all this is to say that when we think about progress in neural networks in research and application, they all sort of correspond to innovations in system composition, right? So we talked about the neural networks themselves are systems that are described by differentiable programs, right? And new ways of composing, such as transformers, are where a lot of the innovation comes from. New ways of thinking about teaching machine learning models are all about sort of building systems which compose data producers and different sort of learning procedures. And finally, to pull this together into an application is all about sort of integrating models into distributed systems spanning multiple runtimes. So zooming back out from that original view of kind of neural networks is sort of like one algorithm among sort of multiple machine learning algorithms, we can kind of shift our view to kind of think about neural networks through the lens of an emerging programming paradigm, right? And what we're doing on a day-to-day basis was we're building systems around this emerging programming paradigm of sort of differentiable functional programming, right? And a lot of where the innovation is coming from is through the ability to create systems. And by composing systems in different ways, we arrive at new results, new kinds of models. We arrive at sort of new kinds of systems, new kinds of application capabilities. And so here's where we come back to this idea of typed functional programming, because typed functional programming is all about giving us tools to make systems that are composable, be able to encode invariants in the type system, and it gives us a lot of sort of expressivity to create systems. And a lot of times when we talk about machine learning, we don't acknowledge this fact that at the bottom of everything we're doing is we're building systems out of these using this differentiable programming approach. And Hasktorch's goal is really to kind of enable type functional programming in this system design space. So this is all very well and good. So this kind of high level sort of philosophical discussion of what we're doing when we're doing machine learning. Now let's get into the nuts and bolts of how do you make that practical? Because there are definitely a lot of practical issues to solve. At a first cut, there are all sorts of hardware backends, right? So to really train these neural networks, you need GPU support, and then on top of the GPU support, you need a huge swath of different mathematical functions, and that all takes a huge amount of resource to build up that stack from the bottom up, right? And so the approach we take with Hasktorch is to piggyback on PyTorch. And for those that are not familiar, PyTorch is really probably the most popular Python library for neural network researchers. And it's built out a lot of these computational backends and library functions and automatic differentiation capabilities are already built into PyTorch. Not only that, PyTorch is separated. You can kind of think of it as separated into sort of this Python front end and the C++ backend. And the availability of that C++ backend gives us a starting point from which we can bind to the C++ backend, and we can build higher level sort of native type functional programming abstractions and explore where that takes us in implementing these machine learning systems. So there's a deeper dive on this by our collaborator Junji Hashimoto from ICFP a couple years back on sort of this idea, but at a high level, we start from what's called Libtorch, which is the PyTorch C++ library. And for the low-level part of the library, we have code-generated Haskell to do the raw bindings and also take care of some memory management. And then on top of that, we can build out sort of the higher level API that end users would use to build models. This API is kind of split into two parts with kind of two different purposes. The untyped tensors, the idea there is really to just have parity with sort of PyTorch functionality. So to be easily be able to import sort of new functions and operators that are available in PyTorch, but leaving tensors sort of as an opaque object. Then there's type tensors, or now Torsten's been working on gradually typed tensors, where there's an explicit type level representation of the tensor shape. And there's a lot more sort of type level exploration of type level computation of what can you do when you are sort of explicitly representing tensor shapes in the type system. And so on top of these APIs, then you can build sort of training procedures, models, and then embed those models in applications. So what does it look like to work with Hasktorch? So coming back to this view of sort of machine learning as functional programs, we're able to kind of have model implementations that look a lot like this sort of conceptual model of machine learning. So for example, here is a simple MLP. So these are just basically stacks of linear layers. Really what you're doing is you're just, you implement that exactly. And sort of that first parameter there is really the parameter state that gets passed in, and it returns a function corresponding to a multi-layer perceptron computation. Here's kind of a simple description of a variational autoencoder, and again, sort of the first parameter that sort of queried is the parameter values for the neural network, and it returns a function that performs the variational autoencoder function. Here's another examples where you use the native Haskell sort of composition operators to build up neural networks as compositions of function in Haskell, right? And here's a more complex example. This goes back to that transformer architecture I showed in the early slide. And one thing that's different about this is using Torsten's work on the gradually typed API. And you see there's a little bit of type level trickery going on where it's marshalling sort of type level values into value level values around shapes and things. But overall, the computation is still kind of reflecting the composition of the model architecture here, right? So we talked about kind of the inference computations. The parameters themselves can be represented as algebraic data types fairly naturally in Hasktorch, and these can be nested in one another so that you can compose neural networks out of modules of kind of subcomponents that are also themselves algebraic data types. We can also take advantage of generics to do a lot of automation of boilerplate, for example, for parameter updates and things like that, so that you don't have to kind of rederive this boilerplate for every new model that you implement. There's a lot that you can get for free with using Haskell's generics. And finally, you can have common machine learning patterns models as type classes. So for example, this forward function defines the ultimate kind of inference computation for a model, and you can abstract that out into a type class, so you can write code that's sort of generic across different models that are kind of writing against these sort of type class interfaces. I mentioned one of the things that neural networks depend on is this capability around automatic differentiation. And automatic differentiation basically takes any sort of function that's within the library or composition of functions, and for a given data point gives you the gradient at that data point, and then you can use that in your optimization procedure. So that we get for free by binding to Libtorch. I know there's a lot of work in sort of the functional programming world to make sort of the representation of automatic differentiation more explicit, and that's something we can explore in the future of having that kind of automatic differentiation procedure explicitly represented. But for now, we can sort of piggyback on the capability that Libtorch provides us to get these gradients for any sort of Libtorch function or any sort of composition of Libtorch functions. And then sort of putting this together to train a model. So training model is basically just becomes folding over data. There's a little bit under the hood here where this run step calls the automatic differentiation and updates parameters and gets a new set of parameters. You update the parameters, and that's really kind of your basic training procedure. Of course, you can start from this and get a lot more complex in terms of going back to kind of these examples of federated learning, of connecting training procedures to generative processes or things like around synthetic data or simulators. But this is kind of the basic structure of training a model. And these examples so far are primarily for the untyped API. For a deeper dive on kind of a more in-depth tutorial, I encourage you to check out this Literate Haskell tutorial by Matt Wittman. For now, most of the tutorial is around the untyped API, but as we do more work on that gradually typed API that Torsten's working on, there'll be more material there too. Right. So I've talked a lot about sort of the kind of basics of what it's like to work with Hasktorch. I want to kind of go up one level. We talked about training a little bit to what it might be like to start building applications machine learning applications, right? And so we talked about some components of this in the earlier slide, where these applications are basically you kind of push and pull these serialized models into a service runtime, into Edge. And so what's that like in Hasktorch? One thing to be aware of here is that there's a lot of tooling around sort of representing models as serialized artifacts. And we can piggyback on that in order to be able to interoperate between languages. So we can take a model that's trained in PyTorch and reuse it in Haskell. And so that gets us around kind of this issue that, even if we have Hasktorch, maybe it just seems like it's prohibitively expensive to train this computationally intensive large language model. But in actuality, we can sort of take the weights, load them up, and integrate these capabilities into our Haskell programs. So to get a sense of how it's doing that, sort of going back to kind of our representation of models, you can kind of think about these separating model into sort of parameters and computation. And the parameters are represented in the PyTorch world by the state dictionary that has sort of all the model weight values, and the computation is you have this torch script intermediate representation that you can use to represent kind of a model computation. So there's kind of different ways in which you can mix and match. So if you're working entirely within Haskell and you're training models with Hasktorch, you can always use basically saving and loading of parameters, and that can let you kind of go from being in sort of your training mode to then loading the parameters at within your, say, servant API or other web API to then load the model and run the model computation once it's been trained. If I'm going back and forth between Python and Haskell, I can take advantage of this torch script function ability to extract out the state dict sort of parameter values as well as a computation graph. And if all I want to do is, say, use Haskell for deployment, it's actually quite easy to just, with this kind of one-liner, load the torch script intermediate representation of a model and basically call the forward function, and then I can immediately have that sort of Python PyTorch model running in a Haskell application. If I want to do a little bit more with the model, like let's say I want to fine-tune the model a little bit more, I want to train it a little bit more, I want to introspect the insides, rather than loading the computation as sort of this opaque intermediate representation object, I can also parse the parameters into a kind of Hasktorch model. And this is what you do if you want to kind of pull out sort of different values, or if you want to kind of update the model some more, you can take this approach. So kind of pulling that all together, you can, once you load a model, then you can use it just like in any kind of standard API. So here's an example using servant and then calling out to servants to stand up a web API, and then calling out to Hasktorch to run sort of the model inference on some parameters that are specified through the API interface, right? If you're interested in kind of this aspect of sort of integrating models into APIs and building applications around them, you can take a look at this small sort of mini tutorial series under examples, model serving. There's a sequence that goes through some of this in more detail. So I want to kind of, before I wrap up, talk about sort of some of the ways that Hasktorch gets used. And primarily it's by a great community that's sort of exploring these two different directions, right? These two directions of, one is, what are some of the things we can explore that's at the intersection of machine learning and programming languages? How do we kind of put type systems around neural networks, and how can we kind of express neural networks in new ways? And second is developers that are interested in sort of building machine learning systems using the tools of functional programming. And so we've had lots of community members and collaborators that are exploring pretty interesting things. So Chiara had an Europe's paper around program synthesis. Jesse did a Google Summer of Code with us around Naperian functors. Torsten's been exploring the space of gradually typed neural networks and really kind of looking at sort of pushing the boundaries of Haskell's type system by expressing these really large language models like BART and BERT, and representing all these shape relationships using the type system of Haskell. Personally, I've been working on using embedding Hasktorch in applications, and one that I recently open sourced in sort of a pre-alpha stage is a sort of a personal knowledge integration platform. That's one of these kind of second brain knowledge gardens. And one thing that's different about this is this application is meant to be self-hosted. And the idea is to have the API is written in Haskell. And the idea is to have something that's self-hosted and enables these kind of machine learning integrations around NLP in a way that can be sort of personally owned as an application. And part of that is using SQLite as storage medium. So if you're interested, take a look at the GitHub repo for that. So with that, I just want to call out if people find this interesting, want to contribute, definitely join our Slack. You can take a look at our website at hasktorch.org. You can look at the main repo and as well as a project template. So yeah, so thank you for your time, and I'll definitely be happy to take questions, and I'll see you in the meeting room afterwards as well.